6.
Number 20. 15.
15. $15?
Yeah.
Okay. Let's see. Oh, yeah. That's all I'm going to say. No,
That's all you're gonna say?
no,
Oh, yeah?
I'll check. So, I don't care what the function is or the equation that we're trying to solve. You always do the same stuff. And I know you don't believe me, but what term has my variable in it? Yeah, the first one, right? Negative 8 times 10 to the... I need to get that thing by itself first. So what do I want to move first? Negative 7. Yep. So first I would add 7 over, right?
Yeah.
Okay. So then you get negative 8 times 10 to the p plus 7 equals
Negative 17.
negative 17. Now you want to do what?
Divide negative 8.
Divide by negative 8. So whenever we solve any equation, we're stripping away all the shit that's on top of my variable. Because we know we want to stop with p equals a number. So I'm going to strip away all the shit that's not letting me see what p is. So if I do that, I'll get 10 to the p plus 7 equals 17 over 8. Now normally, what function, well, let me say this a different way. Let me take one step back. Where's my variable? Where's my variable? In the exponent. What's the only function we know of that could help me with that? That could get that free?
Log.
Some kind of a log. I normally use natural log. But why does something else make more sense?
Because there's a 10.
There's a base of 10. So what logarithm am I going to use? Log. Everyone knows it's log. So if I take the log of both sides, that's going to kill these, yes? And then you can figure out what p is. This business, you're just going to throw in the old calculator and let it chew it up, right? So now you have p plus 7 equals this business. Whatever that business is, I'm going to subtract 7 away from it. Okay, I see some recognition. Okay. You guys, so that's basically the way all of those work, except look at number 21. That's the one I expected questions on. 21, 27, these kind. So let's do this. Let's do a real quick review. Okay. Can anyone tell me why this problem is not that terrible? What do I do to both sides?
You just have to put the log, so log, or x log 4 equals...
Yeah, so if I take the natural log of both
Or,
sides,
yeah, natural log. And then you just divide by natural log of 4.
yeah, so you get x equals this business. And that's the exact answer, and then you can throw it in the calculator and get an approximation. 11. And I could do that because I could get this by itself. So a problem like what we just did, I don't know, negative 11 times 15 to the x minus 1 equals, or let me say, plus 2 equals negative, what do you got, Jeff? Negative 20, sure. You rewrite that. Negative 11 times 15 to the x minus 1 plus 2 equals negative 20. Now, that is much worse than this was. So this one started off as 4 to the x equals 11, right? Why was that so easy? Because my variable piece, it's by itself. I can attack it directly. Here, there's what my variable really is, right? You guys with me? So again, I need you to understand, whenever we solve any equation, we're trying to make it look like a similar equation that's easier. There's a lot of extra shit going on here. What's the very first thing I want to get rid of here? The 2. Because this term has my x in it, so I want to get it by itself. So I'm one step away from it looking more like this. That was relatively easy, right? What do?
That's kind of hard to read with the stuff on it.
Sorry? Oh, I'm sorry. Remind me when I do that. I am not a projector user much. I don't mean to make the difficulty level higher. What do I do now? My variable's here. What do I want to get rid of?
You move 11 over?
How do I do that? Yeah, I don't add because it's multiplying. I got to divide by negative 11. 2. And now it looks basically exactly like this did, just like one little bit worse, and it's barely worth even worrying about. It's got a -1, so I'm going to add 1 at the end. What do I do to both sides?
Log?
Yeah, take some kind of a log. That comes down, and I can divide by that. Is that all right? Just skip a step. If that comes down, and then I can divide by ln 15. You guys all with me? And then I just
Add 1.
So x equals this business here. That's the exact answer, and then I can throw it into the calculator and get a decimal approximation. One quick little thing. So we got that. What if I ask you, what if I ask you to do differential equations? What if I ask you this question? Yeah, there. First step.
Start with a 5.
Good. Do what?
Subtract it from both sides. And you're going to go log.
Am I? Well, if you try to, your calculator's going to freak out.
Oh, yeah.
So this is saying 8 raised to a power equals a negative number. What does an exponential equation look like, a function? If I graph it. Can you guys do it in the air? What's it look like, exponential? That's a parabola. That's a quadratic. That's a cubic. That's a dinosaur. There it is, okay. I love you guys. And people doing this. What is that?
Walk like an Egyptian.
Listen, guys. All right, I love you so much. And you're all like, we love you, Jeff, so much. So guys, if we understand what the graph of a function looks like, we can handle any question about it much easier. From the graph, are there any negative outputs? Can this equation have any answers then? No, done. Done. No answer, no solution. Done. Yes? You guys understand? If you keep going, you should get an error in your calculator, and what people normally do is they just take the negative off because they think, well, I must have made a mistake. No, there's no answer to this. There's no way to make that happen. Okay. And we all need to be at a place where we're so fine with that. I can set up an equation very easily that has no solution. So an equation having no solution is not a surprise to us. Right? And do you see the comparison? If I know what the function looks like, I know what it's not allowed to equal, which means if the equation is trying to say it equals that thing, I know there's no solution. There's no way for that to happen. So the better we know the graphs of functions, the better I can just answer this question without doing barely any work. I'm done. No solution. Whatever. This one, what would these look like if you graphed them? I just gave it away, sort of. It didn't mean to. They're little arrows, but what would they look like? Straight lines. Can anyone tell me the slope of each?
1.
1. Do they have the same y-intercept?
No.
No. So what kind of lines are they?
Parallel.
Parallel. Can they ever equal each other like this equation wants them to?
No.
That's another reason why there's no answer, because there's no way that those graphs could ever meet like the equation wants to have happen. You guys see what I'm saying? There are multiple ways to look at a problem. Now, if I just solve the damn thing, I get the algebraic answer, 1 equals 2. Can't happen, no solution. Because the way to interpret an answer to an equation is, when this is true, this is true. This is never true, so this is never true, so there's no x that saves the task. There's no solution. Nothing will make that true. Okay. I like it. Now you're all like, when's the next spring break? No. It's too bad. Anything else before we get into new stuff? Is that all right? One last little review thing. Why is this question really, really easy? This equation. What can I do with that equation?
Just put it in exponential form.
Yeah, I could put it in an exponential form. What would the exponential form be?
4 2 equals x.
Say it, sorry.
Squared equals
4
x.
squared.
4 squared equals x, so x is 16.
Yeah.
So you're like, please give me a ton of that shit, Jeff. Make them worth everything. No, too bad. So what's wrong with this one? Oh, let's see, Jeff. Can you make one that works? I don't know. Oh, okay, I think that should work. Okay. What is fundamentally different? What makes this one worse, obviously? Why is it different? 2 freaking logs, right? That's a quick way to answer my crazy ass question. It's 2 freaking logs, Jeff. So this one was easy because I know how to rewrite log equals number. I have no way to rewrite difference of logs equals number. But how can I rewrite difference of logs? Good. So what will be on the inside? Good. Now it's the same shit. The thing you have to get over is, yeah, I know this is worse. I don't care. Whatever the hell is here, how do I rewrite this? How do we rewrite it? Same way. 4 to the first is?
X over x minus 2.
And then I multiply this up, and then it's really easy to solve. Are you guys at all?
Because 4 to the first is 4.
Yeah, kick ass. Okay, maybe. So most equations, we're trying to rewrite it in a way that it's in a form that I know how to solve. That's what we're doing a lot of the time, right? Okay. So just, if you were curious, so this would be 4x minus 12 equals x. Subtract x, add 12, I get x is 4, and then if I check it, it works. Okay. That's kind of how I created the equation. I just started with the answer, and I set up an equation that I knew would work. Okay. All right, guys. Oh, sorry. What happened?
Yeah.
You got to tell me when you're doing that paparazzi.
Yeah, I'm trying to photograph that because I can't write that.
Look at this. Okay. Anything else from old stuff? We're about to take it. I don't want to overhype this, by the way. I'm sure you guys know something about what we're about to get into. Do you remember how anybody feel better about logarithms than they did before we talked about them, or no? You don't have to lie to me, it's okay. If I didn't do a good job, you could just tell me. You suck, Jeff, I hated the log stuff. Great. I desperately, what's a log? What's the answer to a log?
It's unexplained.
What's the answer to a log? A power. If you just remember that, every question on a log is much easier. Not easy necessarily, but easier. So if I say log raised 3 to 9, you're thinking, what power does 3 need to make 9? So it's just internalizing the question that the symbol represents. The symbol sucks. Who the hell wanted to use a word, log, as a symbol? Too bad, we can't go back in time. Not yet. If we could, you're right there. I didn't, so I didn't create time travel. Damn it, Jeff. So, since we can't go back in time, we have a horrible representation, but we just have to internalize the question. When I ask you a square roots question, you've internalized what the symbol means. You don't even translate it, you just do it. That's how any language works. So logarithm, you just have to remind yourself, oh, it's asking me for the power. Okay, now I have a way to attack the problem. Okay. So, what we're about to get into is trigonometry. I know some of you guys have done some trig before. Has anybody never really done any trigonometry before? So when I say sine and cosine, have you heard those words, but do you know what they mean? Okay. All right. Very first thing we're going to do is just kind of a quick rundown of angles. Right? We're going to learn some new stuff on the way, but let's start with some really basic stuff. Can you guys all just draw an angle? What would an angle look like if you drew it? Draw an angle for me real quick. Bless you. So I'll make one. There. You guys all with me? Where's the angle part of this, by the way? Where is the angle part? Assumed to be. It's in here, right? So I always think of it how wide a mouth is open. Yes? So that's going to come up again later in terms of how wide a mouth opens and putting a stick into it and all that stuff. We'll see that later. So if I wanted that mouth to open wider, I would just have to make the space between the initial side and the terminal side bigger. So in this case, I can consider this. So if I did my arrow like this, let me do this bigger. If I did my arrow like this would be the initial side. And then I've rotated, and this is the terminal side. I am not too concerned about those words. They're not going to come up a lot. But they will come up every now and again, so just in case they come up, you know what the hell they're talking about. That is considered a positive rotation, so for some reason, again, just the same people that came up with log came up with, let's say positive is going counterclockwise. That's dumb. Oh well, too bad for us, right? We could have made it go the other way. We could have totally built everything on terms of that, but no, too bad for us. They wanted to go the other way. Great. Is everybody with me? So that would be a positive angle that it's gone through. If I go backwards, it's a negative angle. So this, let me see. Can you guys, what would be special about a 45-degree angle, for example?
Well, there's two of them makes 90.
Where's a 90-degree angle in here? But if this is my initial side,
90 degrees at the
where would my terminal side be? Sorry?
At the origin.
That doesn't make any sense.
no, sorry, that's the angle.
So my initial side is this x-axis, the positive x-axis. To make a 90-degree angle, where would my terminal side be?
It would be the
Y-axis.
The y-axis. Good.
Could be either
So
positive or
this would be 90 degrees. So where's 45 degrees?
right in between it.
Right between them. I love it. So this would be roughly 45 degrees. Okay. I like it. So of course, how many degrees if I go all the way around?
360.
360. Why?
That's just what you.
It's just what it is. I need you to understand this. Everybody in here understands that in a circle, they go all the way around to get 360 degrees, yes? Do you know why?
Has somebody decided this?
Yep, we stole it from the Babylonians. What's our number system based on, for some reason? 10. I just don't know why. I have no idea why it's based on 10. The Babylonians, very quickly, we're not going to learn Babylonians. and I'm kind of sorry for you because they're really nifty. But Babylonians had a base 60 number system. Babylonians are the one that came up with minutes and seconds, the idea. So we stole that from them. And they also came up with degrees. 360 degrees has how many factors relative to other numbers? It's got a shitload, exactly. A metric shitload, right? I guess that all with me. I can break 360 degrees up multiple different ways, yes? Very easily. If we had made it 271 degrees, that would have sucked really bad. Okay, so very sort of. I need you to understand. We could have made it 400 degrees. That's a pretty good number too, right? Can't I divide 400 by a lot? We could have just made it 400 degrees. There is not a damn thing special about 360, except I could break it up in a lot of different ways. It could have been any damn thing we wanted it to be. Is everybody with me? So in that respect, degrees suck. They don't have any physical representation, really. They're not tied to something physical. They're just the number we picked. That is nothing special. So one thing we're going to do in this first section is we're going to develop a better way to measure an angle that actually means something physical, not just some made-up bullshit. Okay, maybe. I have no problem with 360, by the way. It's fine. But you quickly understand, after we do a little bit of this stuff, you'll go, why the hell did we ever do that? I don't know. Okay. Okay. Shiba. So let's do a couple things about angles. If I say that I always start here, this is 0 degrees, this would be 90, 180,
360. Oh, sorry, 270.
270, I love it. So you're just basically adding 90 all the way around, right? And so this will be 360. Now, real quick, couldn't I just keep going until I go a little more insane than I currently am? What if I went backwards? Like I said earlier, what else is this one known as? If I just start here and I go backwards.
Negative 90.
This is also known as negative 90. This is also negative 180. And so forth. Forever. Is everybody with me? So that seems really, really, really silly. It really does. And the reason that this makes physical sense is if I start looking here, if I say this is 0 degrees and I want to turn by negative 90, I'll go here, yes? You guys still with me? But if I want to turn by negative 450, can anyone tell me where I'm going to end up looking? Negative 450. How many rotations is that? A full rotation. How many full rotations? It's one full rotation, yes? And how much do I have left to go? Because I just went through how much? Just now, I went through how much? 360, negative 360. How much more do I have to go get to 450? 90. So negative 90 and negative 450 are the same damn things. Shit. I feel like I did last week. All right. You guys all with me? So there are an infinite number of ways to represent any angular direction. Now, in one sense, that is dumb. Does everybody agree with me? If you tell me to go 1,080 degrees, I'm not going to spin. I'm just going to go to where that would be, right? What would 1,080 degrees be? How do you figure that out?
Divide by 90.
Say again?
Divide by 90.
Mm,
And then that's how many quarter turns you do.
no, there's a better way to do this. Isn't that a bunch of full rotations? Don't I just subtract all full rotations until I can't anymore? So if I subtract 360, what's that? You can do it.
720?
720. If I subtract 360 again, that's
360?
360. If I subtract 360 again, that's
0.
0. So if somebody wanted me to rotate through 1,080 degrees, I'll just say, okay, I'm done. You guys sort of, because now I'm facing where I'm supposed to be facing. Okay, maybe. Okay. Now, real quick. We are going to stick in 2 dimensions, correct? But if I brought a 3rd dimension, this makes a lot more sense. Have any of you ever gone into a parking garage that had one of those spiral ways out, right? Or you've seen them in movies, right? You guys will, hopefully you don't do that. That's fine. So isn't that just going, turning? If I look from above, doesn't it look like cars just going around in a circle? Yay! But aren't I ending up at a different position in the third dimension? Yes? But in these two dimensions, I'm just going in a damn circle. Are you guys at all with me?
Yeah.
So once I add the third dimension, this makes more sense. Now if I go through 1,080 degrees, I'm going to end up at a different level in this dimension. Okay, I don't want to do too much of that because we're not going to do 3 dimensions. But just to show you how this multiple angles mean the same rotation physically means a different location. Okay, maybe. Okay, now. Blah, blah, blah. By the way, before I get too far, just to do a little real basic trigonometry or geometry. I could keep going forever, correct?
Yeah,
And that would not change this angle at all, yes?
correct.
Anyone know what the geometric name is for this thing here? It's not a
Ray.
line.
It's a ray.
Ray, I love it. And this is a ray. Crazy. So if I take one ray, I'm going to say ray AB. And I put another ray with A as the, so this is ray AC. How can I define that angle? I can call that angle BAC, I can call it angle CAB, or I can call it angle A. They all mean the same thing. If you stop for a minute, hopefully you guys have all gone through some kind of geometry in your life. Let me throw a word at you. Transversal.
That's
Does that name sound familiar to anybody? Parallel lines, transversal, alternate interior angles, corresponding angles. We're not going to do all that, okay? Just wanted to throw that at you. Because I'm evil. So, real quick. One reason we have multiple ways to describe an angle is, what if I had this situation here? What would this angle be right there? I love it, ADB. Or BDA. What would angle D mean? Would angle D mean anything?
ADC?
It means nothing, because it means everything. It's not
Oh.
specific enough. Do you guys see that?
Right.
Here I could call this angle AY,
Because
because there's only one possibility for it. Here, angle D could be this, it could be this, it could be this whole thing.
Right.
What if I want the whole thing? What would that be? No, not the measure of it. How do I name it?
ADC.
ADC. Or
CDA.
CDA. As long as the middle one is the actual vertex. Okay, let me stop for a minute. You guys all with me? This is nothing too groundbreaking yet. Okay. Okay. So coming back to what I was talking about a minute ago before I forget, there's the idea of coterminal angles. I always forget to give you the terminology. But so for example, 10 degrees and 370 degrees, do they end up pointing you in the same direction?
Yeah.
If I started the x-axis, go through 10 degrees versus going through 370 degrees. Why do they end up being the same direction?
Because they're exactly 360 apart.
Yes. So 10 degrees, 370 would be 360 plus 10. So I'm going to end up looking the same way. So we call those coterminal, because once you're done spinning, you're facing the same damn way. Coterminal. Same, stop. Right? Okay, nothing too major there. I love it. So if I wanted you to figure out a good coterminal angle of, what do you got, Jeff? 857 degrees. We just did this a minute ago. What do you think I would do?
Subtract 360.
Yeah, the funny thing is, if you divide, that would work. If you did it correctly, you could just subtract 360 until you can't anymore, right? Is that right? I think it's right.
Close enough for government work.
Close, yeah, exactly, that's what I do. Okay. It seems wrong. Just because it's a 6, Jeff. Good job, buddy. There we go. Still seems wrong. Because that's a 7, Jeff. It's unbelievable. Okay, I'm still coming back. Okay. Should be 497, Jeff. Okay. Just unbelievable. I'm just showing off now. Okay. Now, real quick, just to show you, if you did divide by 360, just want to point this out. Because I don't know if you guys, real quick. Multiplication is repeated addition. Division is repeated subtraction. So what is 857 divided by 360? You're going to get 2. Point stuff, right? Okay. Can everybody do this if you have a calculator? Can you guys do it real quick? 857 divided by 360.
2.380.
Yeah. Real quick. This is kind of awesome. Come on, little calculator. It's got to wake up from a long slumber. There you go. 857 divided by 360. Now watch this. You ready? Everybody do this that wants to do this. Minus 2 times 360. It shouldn't be that surprising. Don't we get the same answer?
137.
Because what is 0.38 bullshit? What is that 0.38 blah blah blah? That is the remainder written as a fraction, correct? Is some number out of 360. Are you guys with me? And if I'm dividing by 360, won't my remainder be over 360? So if I multiply that piece by 360, I'll see what the remainder is. In this case, 137. Yeah.
So would the 2 be like how many times you subtracted 360?
Exactly. How many rotations? Exactly. So that's why division is repeated subtraction. The answer to a division question is how many times you have to subtract that number until before you get negative, right? I like it. Okay. So let's talk about units for angles. Let's develop some better units instead of degrees, because degrees are just made up bullshit. So how many total degrees are in a circle again? Yeah, 360, right? How many, if the radius of this is r, let me do this. What's the circumference of this circle? Does anyone remember?
R squared. Oh, yeah.
That's the area. Area is always square units.
2 pi r.
2 pi r. Does that sound familiar? In fact, really quickly, guys. I say that a lot. Does anyone know where pi comes from? Yeah, no,
That's the ratio between the circumference and
yeah.
diameter.
So civilizations, because they didn't have like cell phones and shit, they focused on weird things like, no matter how big of a circle I have, if I take the circumference and divide by its diameter, you always get the same number. So that freaked the hell out of them, right? Because they didn't have anything else to think about. So no matter how small or how big the circle is, the Earth isn't really circular, but if I imagine chopping it and looking at this, what's there, I'd get the same number basically. So when I divide the circumference by the diameter, right? Yeah, circumference divided by the diameter, they always got the same number. So the Egyptians actually estimated to be 22 divided by 7. So what is 22 divided by 7? 3.14, blah, blah, blah. What do you get, blah, blah, blah? Anybody?
3.1415.
No. I don't think that's that good.
What's the
22 divided by 7?
3.142857143.
Now, it's pretty damn good for a freaking ancient civilization, yes? This is the ancient Egyptians, not the current Egyptians. And then other people, the Greeks had their own approximations and so forth. So nowadays we have supercomputers that just spit out millions of places. We have people, do you guys know there are people that memorize like 50,000 places upon, like, my God. No. I love math. I ain't doing that shit. I know 3.141596, that's it. So on March 14th, 2015, that was what we called Super Pi Day. So we all geeked out, all the math people. And you're like, ooh, you lead such
Yeah, I got
awesome
it.
lives. Yeah, Super Pi Day. Anybody ever hear that before? Do you guys all know where pi came from? That's where the equation came from. If I just multiply the d up, I get this. So where's the r then? Well, the diameter is always how related to the radius?
The radius is half the diameter.
Half of that, so it's twice the radius. So there's the equation for circumference. Okay. So coming back to this. Circumference is 2 pi r, and I go through 360 degrees when I do that, correct? So here's something kind of cool. The circumference, does everybody agree with me? The circumference is a physical measurement. It's a real thing. I can walk it, yes? Degrees, I made them up. So the circumference is going to be related to what we use for a better way to measure an angle. So, if I have a circle. Oh shit, what else is down here? Oh, more differential equations. Okay. Here's the radius. Now, I'm going to do something kind of weird. Come down here. All right. I'm going to take this radius. I'm going to bend it. And then I'm going to put it back on the circle. Well, that's not going to work, but oh well, I'm trying. Almost. Not really. Maybe do this a little better. So if I took this and I bent it so that it fit on the circle, this is an angle, correct?
Yeah.
If I walk along any circle, I'm going to walk through a certain angle. Is everybody with me? This is a physical measurement. This is something I could do, yes? So if I took the radius, it needs to be a little bit bigger. If I took the radius and I bent it and I put it here, how many, let me say this wrong first. How many radiuses, how many radii did I just walk? I took one radius and I plopped down. How many radii did I just walk? One. So we call this 1 radian. And the crazy thing is, if anybody's concerned about what if it's a bigger circle or a smaller circle, if I have a smaller circle, isn't the radius smaller? So if I take it and bend it, won't I end up at the same relative place? So this is still 1 radian. So using the radius of a circle to define the angle itself makes more sense. It's a physical measurement, not just some made-up bullshit. I don't know if you guys are really with me. So I don't care how big your circle is. If my circle's bigger, whoa, how far do I actually walk to go through 1 radian? I walk a longer way, don't I? But how big of an angle did I just go through? 1 radian. I love it. We stop for a minute. This is kind of related to the idea that this angle is so big and it stays that big. I don't care how long I take those out, the angle doesn't change, correct? That's exactly the idea we're capturing here. So radians are a better unit for angle measure. They're not made up bullshit. They're actually physical things. The further we get into trig, the more you'll see why that's important, right? Okay. So, real quick, let's talk a little bit about radians. Now, does everybody get the basic idea? This is such a cool idea. I could be alone, but it's just so awesome to think about. Take the radius, bend it, put it back. There, I'm going to define that to be how I talk about it. So, if I went two lengths that were equivalent to a radius, how many radians did it just go through? Two radians. Kick ass. I don't have to make shit up. Because, like I said, couldn't we have made it 400 degrees? Would it really have changed anything? No. I could have made it 80 degrees. I could have made it 6,000 degrees. It doesn't really change. This, everybody would get the exact same thing. Okay, maybe. All right, I love you guys. You're all like, keep going. Okay. Now, with this said, how many total radians are in a complete circle then?
2 pi.
Yeah. Just coming back to my little contented circle here.
If there's 2 radiuses in a diameter.
Yeah, basically what I'm doing as I move along, if this is 2, then it's really just measuring how far around the circle I'm going. Correct? So if the circumference is 2 pi r, what does this really mean? That means to get around the whole circle, it takes this many radii. See if you guys are cool with this. To get all the way around the circle, it takes 2 pi radii. You guys all with me? And isn't that exactly what a radian is the number of radii I've gone? So if I go all the way around the circle, how many radii have I gone? 2 pi. So all the way around the circle is 2 pi radians. So how about halfway around the circle? What would that be?
Pi.
Yeah, pi radians. Okay, maybe. How you guys feeling? Are you guys all right? This is kind of a huge step if you've never seen this before. Okay, that's all radians are. They're so beautiful. It's just the number of radii it takes to get around. If my circle gets bigger, so does my radian. So does my radius, I should say. Then I take the same number of steps. If each step I take is a radius big, then I take the same number of steps to get around the whole circle. Okay, bye. All right, so 2 pi is 360 degrees. Pi is 180 degrees. This is a very useful thing to know. So, those of you, I know several of you aren't chemistry. It's something you all desperately love, besides balancing equations, is conversions, right? These conversions are not going to be horrible, because it doesn't involve Avogadro's number or anything else. It's just like feet and inches, correct? If I wanted to convert 70 inches to a certain number of feet, how would I do that? How many inches in a foot? 12 inches in a foot. The minute I know how many of one thing makes the other thing, I can convert either way I want to, correct? It's just a question of, do I multiply or do I divide? So something I stolen from chemistry. If I had 240 degrees, and I wanted to make that into some number of radians, what unit do I want to kill? What do I not want there anymore? Degrees. So where would I put degrees? On the bottom, so they cancel, yes? And then I would put rads up here. How many radians are in how many degrees? How many radians are in how many degrees? Pi radians are in 180 degrees. Yes? You guys all with me? So real quick on the side, 70 inches is how many feet? Don't I want inches to die? and I want to replace it with feet. So then 12 inches in a foot, I would divide 70 by 12. I get the answer, yeah? Okay, it's like 5 point something other. I don't know. So here, let's just reduce this. Everybody agree that I can divide by 10? What goes into both? Just reduce this bad boy. What's this become? What goes into both?
9.
Say again, what?
2.
More than that.
6.
4.
6. So if I divide both by 6, don't I get 4 pi over 3? If I divide 24 by 6 and 18 by 6, don't I get 4 and 3? Yes, yes, yes. All I did was reduce the numbers. That's all I did. Now, very quickly, if I made this into just a decimal, I would get 4 times pi divided by 3. I would get that funky-ass decimal. 4.19, roughly. So if I want to turn 240 degrees, that's the same thing as turning 4.19 roughly radians. It's the same thing as walking on the circle a little more than 4 radii worth. Okay, maybe. By the way, do you guys notice something very important? If it does not have a unit on it, it's radians. If you want it to be degrees, you better put a degree on it. Yes? That's huge. That's really, really important. So if I write 30 on a test, and it's an angle, what units does it have? If I wanted it to have degrees, what would I have had to put? Degrees. I didn't put anything, so what units does it have? Radians. Good. You guys all with me? Yes?
So the pi over 180, is there other things you could put there instead of?
Oh yeah, you could put 2 pi over 360, right? But why would you? It just reduces to pi over 180. Sort of like you could put 2 feet is 24 inches. You could use that. It would work. But why would you? You want to kind of reduce it. So I reduced it to a whole number of pi's. So I got pi over 180. That's a beautiful way to remember it. But you could put something else as long as it's true. Yeah. Okay. All right. Maybe. So here, you guys, real quick. Please convert 135 degrees into radians. And I want the exact answer, not a decimal approximation.
You don't want a decimal?
Nope. So I want some number of pi's. So first off, where's degrees go?
On the bottom there?
Bottom, so they cancel. Up top I got rads. So then where's 180 go?
180 goes by the degrees.
I like it. So how do I reduce this?
You divide 135 by 180. So it's a degree.
Sort of, but then you get decimals. I don't want that. So real quick, guys, real quick. I think I've talked to you about this. Well, what's 1 plus 3 plus 5? 9. And what's 1 plus 8 plus 0? So they're both divisible by 9, yes? Let's see. If I divide both by 9, I'll do the bottom. Thanks so much, Jeff. What do you get on the top when you divide by 9? 45? And then I can divide both of these by... Is it 45?
5.
That seems wrong. 9 goes into 135.
Oh, it's
15, right? Yeah. Divide both of these by 5, I get 3 pi over 4. That is the answer. That's how many radians. And if you want to, you can put rads, but you don't need to. Because if there's no units, it's assumed that they're radians. Now, just for shits and giggles, what do you get when you put this in the calculator? 3 times pi divided by 4?
0.75.
No.
Oh.
You get 3 divided by 4 is 0.75, sure.
2.35619.
Roughly. Okay, I like it. So what does that mean? That means if I go 2.3562 radii worth across this circle, I will end up at 135 degrees worth of rotation. Are you guys at all understanding what I'm saying? If I go 2.3562, sorry?
You screwed left just a little bit. Perfect. Thank you.
If I go 2.3562 radians across here, I end up at the same thing as 135 degrees of rotation. I need you to get that. If I rotate 135 degrees, I end up looking at the same place as if I walked along 2.3562 radians worth of distance. They mean the same thing. They end up at the same place. Okay, maybe. Let's do this. Let's do something I've never done before. This will be exciting. Okay. I'm going to give you a specific circle. Let's say I have a circle of radius 10, just to make this let's make it 12. Okay. What's the circumference of that circle? Such a beautiful circle, Jeff. Let's try better.
2 pi times 12.
Yeah, circumference would be 24 pi. Is that cool? You guys all okay? So if I go 1 radian around this circle, I'm going to go 12. So 24 pi is roughly what? 24 times pi. 372, so 74 point something.
75.36.
Thank you. So we're just going to make that 75. Okay. So all the way around to 75. If I go 1 radian, that's going to be 12 out of 75, correct? You guys, so let's do this. What would this be? How far would this be? The whole way is 75. How many, let's say this is feet. How many feet would that be? So go here. Oh, is everybody cool that the circumference is 75 feet, roughly?
Yes.
If I round. Okay. So all the way around to 75 feet. So what's this?
75 over G.
Yeah, half the 75, correct?
Okay.
So 37.5? Okay, so what's this? Just this much.
75 over 4.
18.75? Is that right? Okay, I love it. So where would 12 feet be? Wouldn't 12 feet be roughly here or so? So that would be the same thing as 1 radian. So that would be taking a radius worth of a walk along here. Okay, maybe.
So 90 degrees is equal to 2 radians.
So if I went 90 degrees, isn't that pi over 2 radians?
Okay.
You guys with me? And how long is the radius in the circle? How long is the radius in the circle? 12 feet.
12 over 2 pi.
You guys all with me? Yes? So this is 6 pi. And 6 pi is roughly 18 point something, yes? 18.7, 18.8? I don't know. Which is about right here, yes?
Yes.
So if I go pi over 2, which is what we knew this This is pi. This is pi over 2. If I go pi over 2, I do end up going that far. So instead of using degrees, I could use the idea of walking along the circle so many radiuses worth of distance. And that's what I could call my angle. My angle is where I end up rotating through as I walk a certain number of radii. Very physical. Using measurements of the circle itself, not some made up 360 degrees. Okay. Okay. I think you've made the point, John. Okay. All right. So what if I wanted to go the other way? What if I've got 7 pi over 6 radians, and I want to change that to degrees? Let me see if you guys can figure out how to do that. Let me help you out a little bit. There's a shortcut, but let's do it the long way first. 7 pi over 6. And I want to get rid of, what is it currently? What units? Radians. So I want to get rid of radians, correct? So I'm going to put it down here, and I want to go to degrees. So 180 degrees in pi radians. So what happens is really nice. The pi is canceled. Yeah. 6 goes into 180.
30,
30. 30 times 7.
210.
210. So what's the shortcut then? If there's a pi in my radians, what is pi radians? How many degrees? Pi radians is how many degrees? Pi radians
180.
is 180. Because 2 pi is all the way around, correct? Yeah, so I'll replace pi with 180, because that's what the hell it is. Why is it really easy to change 4 feet into inches? What do I replace feet with? 4 feet. How many inches is that? Replace foot with 12. 4 times 12. So what's pi? Radians. Pi radians is how many degrees? Pi radians is how many degrees? How many degrees is pi radians?
180.
180. So then I replace pi with 180. That's the shortcut. I don't have to do the grid if I have a pi sitting there for me. Let's do another one. So what if I had negative, what you gotcha? Yeah, something nice. Negative pi over 3 radians. How would I make that into degrees? Pi is 180 degrees. Divided by 3. What's 180 divided by 3?
60.
60. So negative pi over 3 is the same thing as negative 60 degrees. They're the same thing. Okay, so just to kind of lay some groundwork for later, pi over 6 is 30 degrees. Because 180 divided by 6 is 30. What's pi over 4?
45.
45, because 180 divided by 4 is 45. Pi over 4 radians is 45 degrees. Pi over 3 radians is
60.
because 180 divided by 3 is 60. Pi over 2 radians is
90.
90. Good. Okay. So if we step around this circle, let's go further than this. This is all in this. So let me tell you a few things. Do you see how when I make an XY plane, I've broken it up to 4 parts? There's like 4 pieces of this pie. This is the first quadrant, second quadrant, third quadrant, fourth quadrant. So this is all the stuff in the first quadrant, yes? Because it's between 0 and 90 degrees, right?
Yeah.
So this is 0 radians. This is pi over 2. This is pi. What's this?
3 pi over 2.
3 pi over 2, 11. So no pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. 4 pi over 2 reduces to be
360.
true, but in radians. 4 pi over 2 is 2 pi.
Oh, yeah.
Which again makes sense. How many radiuses does it take to get around a circle? 2 pi of them. Because the circumference is 2 pi times the radius.
A hostess pi.
Say again?
A hostess pi.
Sure.
Hostess pi is like a half circle shape, and 2 of those is a whole circle.
There you go. 2 hostess pi's equals a whole circle. Whatever gets it in your head. Like it. Alright. Has anyone ever worked with radians before today? Few of you guys. Okay. I don't know if this jives with what you've been taught before. If not, that's a problem because this is the reality. So last thing for today, and this is kind of a big thing. We're going to just start to get into this. So the whole first section is just about angles. It introduces a better way to measure angles, which is radians, right? And I know that some of you, if you've never worked with radians before, they suck. And it's just because you're used to degrees. You're not used to radians. They are better. You're just not used to them. I don't blame you. Now we're going to get into trigonometry proper. And the funny thing about trigonometry is we're going to do a lot of shit with it. And it's going to be really easy to forget what I'm about to say. But all trigonometry is ratios of sides of right triangles. That's all it is. That's all it ever is. That's all it ever will be. But we're going to use the hell out of it somehow, right? Have you guys ever seen the people with the little tripods and they're kind of like landing and somebody way over there and that little tripod dude?
Yeah.
You guys know what they're doing?
They're shooting elevations with a
Yeah, surveys.
stadium around.
So they're kind of measuring how much the, because when you build something, sometimes it'll sink a bit. There could be water running underneath something and that'll make the ground go down a bit. So they kind of want to check and make sure that things haven't shifted so much that it's structurally bad. So they come out, they survey, and they use trigonometry because they're just seeing the angles, how the angles have changed from various locations around campus, for example. Okay, you guys kind of, my little brother hates math. He always kind of makes fun of what I do. I love him. So he tells me, for example, he says, do you teach probability? And I'm like, yeah. And he says, it's either going to happen or it ain't. It's 50-50. I'm like, Jim, thank God you didn't become a doctor. What's my chances, doc? 50-50. Shit! All right. But he went around with he shadowed a surveying group when he was thinking about becoming a surveyor, and he said, now I understand trigonometry because you can actually see it happening. So, let me see. If I take a right triangle. So let's take a really nice right triangle. For some reason, this is really nice. It's not drawn to scale, so don't give me shit about it. One thing you have to remember, it's going to come up a lot, is the old Greek dude. What do I mean by that? Can anyone tell me what the last side length is?
5.
Old Greek dude, yeah. What's the old Greek dude? Who's the old Greek dude? Pythagoras. And actually, it wasn't him. He just stole his followers' work and said it was his. He did some, but they did most. And that's the way it worked. Too bad for him. What's the Pythagorean theorem again?
A squared plus b squared equals c
Kick
squared.
ass. So these are A and B. C is always the one across in the right angle. Now, some of you guys might have 3, 4, 5 triangle memorized. I don't know. There's also a 5, 12. So, if I just make up 2 side lengths, I'll bet you anything the third side length is going to have a radical in it because they have to square root. Correct? Certain numbers will combine in a way to make a perfect square. Like I got a 25 from this. Certain numbers. Not a ton of them. I think it's also 7, 24, 25. They're called Pythagorean triplets, or better, they're called Euler triplet, I think. I can't, all right. There. So, real quick, let me redraw this a little bit. I got too much shit going on. So I have this triangle, just sitting there, minding its own business. And I come along, I do some math to it. There's an angle here. In algebra, the most basic variable we use is x. You guys agree with me? Of course you do. In trigonometry, with angle measure, the most basic variable we use is called theta. And this is how it looks. Greek letter theta. Sometimes mine get a little more excited, so you gotta excuse him. Big old pompadour thing on his head. Okay. So just to lay down some initial groundwork. Remember logarithms? And that really sucked that they chose a word to be a symbol instead of like a square root symbol or something? Same thing is going to happen to us in trigonometry. So the most basic, the very first one we normally talk about is called the sine. So you can have the sine of an angle. We normally reduce it all the way to 3 letters, right? So if I want to know what the sine of this angle was, if I want to know what the sine of this angle is, it's defined to be the y side divided by the hypotenuse. If my angle is in the base, what's the y side? Which piece is the y side, would you call it? Can you see an xy plane kind of here?
Yeah.
3 is the y side, does everybody agree? And 4 is the x side, yes? And then 5 is the hypotenuse. So what would the sine of this angle be then? Y side divided by the hypotenuse?
3 over 5.
3 over 5. So sine likes y. Sine is related to the y piece. There's a phrase that I am not a big fan of. If you know it already, you could use it. It just doesn't do you good. It only works for this long. If you remember sine likes y, that takes you through the whole damn thing. If you know SOHCAHTOA, it takes you through this much. Has anyone ever heard of SOHCAHTOA before? Some of you guys might have heard it from me even. And you know already how much I shit on it. Anyway, SOHCAHTOA is fine. You could use it. It's just so, 2 things, unnecessary, and it's only useful for a little bit. I'll give you one more and we'll call it a day. There's also one called the cosine of an angle. And the cosine likes x. So of course, what would the cosine of this angle be?
4 over 5.
4 over 5. 11. And real quick, just because we have these here, what is sine squared theta plus cosine squared theta? Well, let's see. What's sine theta for this triangle? 3/5, right? Cosine theta is 4/5. What's 3/5 squared?
9/25.
9/25. What's 4/5 squared?
16/25.
Interesting. All right, I get 1. So it's going to come up again later. I figured I'll just throw that in here right now since we have concrete numbers. So all sine is of an angle, if it's in the base, is the y side divided by the hypotenuse. Last thing I'll say. I think I've said that a few times too bad. If I made this triangle twice as big, how long would this side be? 10. How long would this side be? 6. How long would this side be? 8. What would the sine be now? Sine likes y, so it'll be 6 over 10, correct? Isn't that still equal to 3/5? So the sine of an angle is the ratio of 2 specific sides. But I don't care how big the freaking triangle is, for a given angle, for a given size of something's mouth. That's a given size. I don't care how long I take those out, it's always going to be the same number. So that's why, for example, sine of 30 degrees is going to become something you have to memorize, because I don't care how big the triangle is that 30 degrees lives in, it's always going to come out to be the same number. It's going to reduce to be the exact same number. That's why there's a sine button on your calculator. Because no matter what angle you put into it, it's going to give you the same answer. I don't care how big the triangle was it came out of. It's always going to reduce to be the same thing. All right. Oh, yeah.
Can you scroll down?
Yeah. All right, guys, that's plenty for first day back from spring break. If you have any questions, let me know. Otherwise, I will see you tomorrow.